You are not standing still. You are moving through the vast architecture of our galaxy. This motion is not just cosmic mechanics, but a story of human discovery within the Milky Way.
For centuries, humanity assumed the Earth was the center of the universe, that the stars were fixed lights embedded in a celestial sphere, unchanging and eternal. It was only in the Renaissance, with the pioneering observations of Copernicus, Galileo and Kepler, that the heliocentric model displaced this Earth-centered view, revealing the Sun as one among countless stars. Yet, even as the solar system's place within the cosmos was reconsidered, the scale of its motion remained hidden. The Milky Way was first resolved as a vast spiral galaxy through the work of William Herschel, who mapped star distributions and recognized the Sun's offset position, and later through Edwin Hubble's observations, which extended our understanding to the broader universe. Each discovery unfolded the layers of a galaxy in motion, placing our solar system on a dynamic trajectory rather than a fixed stage. The Orion Arm, where we reside, is a region of both activity and subtlety. It is a branch of the Milky Way's grand spiral, stretching tens of thousands of light-years and containing a mixture of older stars, newborn stars, and molecular clouds from which new stars and planetary systems are forged. Within this arm, we find familiar neighbors, such as the bright stars of Orion's belt, the nearby clusters of the Pleiades, and vast clouds of hydrogen glowing faintly with the birth of stars. This arm, though not the most massive or luminous, provides a relatively stable environment for the evolution of planetary systems. Its density of stars is modest compared to the galactic core, avoiding the frequent stellar collisions and energetic phenomena that characterize the galaxy's crowded center, and yet rich enough to offer chemical diversity, seeding planets with the heavy elements necessary for life. Our solar system's orbit around the galactic center is a journey of staggering complexity. Governed by the gravitational pull of the galaxy's mass primarily, its dark matter halo and central bulge, we trace a vast ellipse through the galaxy's plane, rising and falling slightly above and below the disk as we go. This motion is not uniform. Variations in mass distributions, gravitational perturbations from nearby stars and clusters, and tidal influences from the spiral arms themselves subtly alter our path. The solar system, far from being a solitary wanderer, is part of a symphony of motion interacting with neighboring systems influenced by interstellar clouds and responding to the unseen architecture of the Milky Way's gravitational contours. Each orbit is a silent testimony to the invisible forces sculpting our journey through space. To understand our motion is to confront the scale of time and space on which the Milky Way operates. Completing a single orbit around the galactic center requires over 200 million years. In the time it takes to complete one journey, entire species rise and fall on Earth. Continents drift across oceans, and the face of the planet transforms dramatically. In our brief human lifespans, the orbit is imperceptible, yet the solar system has already traversed hundreds of previous paths, carrying Earth through regions of differing stellar density, magnetic fields, and cosmic radiation. Each passage through the galactic plane, each traversal of a spiral arm, is accompanied by subtle changes in the influx of cosmic rays, potential cometary perturbations, and the redistribution of interstellar matter. Our trajectory is not merely motion, it is a journey through history writ on a cosmic scale. The velocity of our solar system, exceeding 500,000 miles per hour, defies intuitive comprehension. It is faster than any earthly object, faster than light could cross a planet in a single second, yet imperceptible to us because we move with it. Our experience of stillness is a trick of shared motion. Earth spins on its axis, revolves around the Sun, and together with the Sun, we orbit the galactic center at astonishing speeds. Each calculation of this motion has been refined through centuries of astronomical measurement, from the early cataloguing of stellar positions by Hipparchus and Tycho Brahe to to the precise parallax measurements by Friedrich Bessel, and finally to modern astrometry using space-based observatories. Every refinement has revealed the dynamic nature of our home, showing that the universe is alive with motion and energy far beyond the static vision that early astronomers imagined. The Milky Way itself is not merely a collection of stars. It is a complex, layered structure with a dense bulge at the center, a flattened disk where spiral arms trace their graceful arcs, and an extended halo of stars, globular clusters, and dark matter. Our orbit places us in a region removed from the turbulent core, yet even here, subtle gravitational tides influence the outer reaches of the solar system. Long-period comets, hibernating in the Oort cloud, are nudged occasionally by passing stars or tidal forces as we journey through different sectors of the galaxy. Over millions of years, these perturbations deliver icy bodies into the inner solar system, linking the grand motion of the Milky Way with the microcosmic history of Earth itself. As we traverse the Orion Arm, the spiral structure itself is not static. Spiral arms are density waves, regions of higher star formation that propagate through the disk. Stars enter and leave these waves, experiencing varying gravitational forces that subtly alter their velocities and trajectories. Our solar system rides one of these waves, passing through regions dense with molecular clouds, star-forming clusters, and occasional supernovae. Each passage can influence the influx of cosmic rays, the formation of new stars nearby, and the potential delivery of interstellar material into our system. The motion of our solar system is therefore not merely an orbit, but an interaction with the evolving structure of the galaxy itself, a voyage through regions of birth, death, and cosmic transformation. The history of understanding our motion in the Milky Way is also the history of human ingenuity. Early astronomers could only map stars in 2 dimensions, assuming that they formed a fixed celestial sphere. Herschel's pioneering star counts revealed the flattened nature of our galaxy and the sun's offset position. But the full 3-dimensional motion remained hidden. The 20th century brought revolutionary tools, radio astronomy, infrared observations, and precise spectroscopy, allowing us to measure stellar motions, trace the rotation curve of the galaxy, and finally understand the velocity of our solar system. In doing so, we discovered the necessity of dark matter, an invisible mass dominating the galactic dynamics, shaping the orbit of stars and the structure of the Milky Way in ways we can detect only through its gravitational influence. This motion is not without consequence for our planet. Periodic encounters with dense regions of the galactic plane can increase the flux of comets, potentially driving mass extinction events on Earth. The distribution of interstellar gas and dust influences the solar system's heliosphere, modulating the cosmic radiation that reaches Earth and subtly affecting climate over geological timescales. Even the search for extraterrestrial life must account for this motion, as the solar system's position relative to the galactic habitable zone influences exposure to supernovae and energetic events. Our trajectory is thus intertwined with both the risks and the conditions necessary for life, demonstrating that location and motion within the Milky Way are not abstract measurements, but vital parameters in the story of Earth's evolution. The universe is silent, but within its silence, colossal forces and unfathomable energies conspire to form structures of unimaginable scale. At the heart of our solar system, a blazing sphere of nuclear fire anchors a vast assembly of planets, moons, asteroids, and comets. To stand on Earth and look up at the sun is to perceive only a fraction of its power. Yet this star, a growing orb of hydrogen and helium, governs the motions of everything that shares its domain. Its gravity binds planets to precise orbits, shapes the trajectories of wandering comets, and orchestrates collisions that sculpt the system's very architecture. The sun has endured for billions of years, and it will persist for billions more, a constant presence around which the drama of the solar system unfolds. Yet even this familiar star is a reminder of the fragility and scale of existence. Without its gravity, planets would drift aimlessly into the void without its energy. Life itself would never have arisen. The Sun is no ordinary star, though by cosmic standards it is modest. It belongs to the middle class of stellar mass and brightness, neither a giant nor a dwarf in the galactic census. Yet its internal furnace converts millions of tons of matter into energy every second, a transformation that lights planets, drives winds, and fuels chemical reactions that sustain life. In its outer layers, turbulent convection creates granules of roiling plasma, magnetic loops arch across its surface, and sunspots, darker and cooler than the surrounding photosphere, appear and vanish in cycles that repeat roughly every 11 years. These sunspot cycles are more than curiosities. They reflect magnetic field fluctuations that can drive solar storms, coronal mass ejections, and shifts in cosmic ray flux that influence planetary atmospheres. For humanity, understanding the Sun has been a quest of survival as well as knowledge. From Galileo's first telescopic sketches of sunspots to the modern era of space-based observatories monitoring the Sun in unprecedented detail. Orbiting this blazing heart are 8 planets, each unique, each sculpted by its own history of formation, collisions, and evolution. Mercury, closest to the Sun, is a world of extremes. Temperatures swing from searing heat during the day to freezing cold at night. Its cratered surface tells the story of relentless bombardment in the early solar system, while evidence of ancient volcanic plains hints at periods of internal activity long past. Mercury's magnetic field, though weak, reveals that even the smallest rocky planets can retain some internal dynamism. Venus, shrouded in a dense atmosphere of carbon dioxide and sulfuric acid clouds, offers a vision of planetary extremes. Its surface is a furnace hotter than Mercury, despite being farther from the Sun, an inferno fueled by a runaway greenhouse effect that transformed its oceans into vapor long ago. The study of Venus provides crucial lessons for planetary climatology, emphasizing how subtle shifts in atmospheric composition can alter a planet's destiny. Earth, our home, is the crown jewel of the inner solar system. Its liquid water, oxygen-rich atmosphere, magnetic field, and temperate climate are not coincidences, but the results of precise balances. Positioned within the Sun's habitable zone, Earth receives just the right amount of radiation to allow water to remain liquid, a fundamental requirement for life. The planet's axial tilt creates seasons, its geologic activity cycles carbon through rocks and atmosphere, and its magnetic field shields life from harmful solar and cosmic radiation. The Moon, Earth's constant companion, stabilizes this tilt, moderates tides, and indirectly influences the development of ecosystems. Understanding Earth in the context of the solar system reveals the delicate interplay of forces and conditions that made life possible, and highlights the rarity and fragility of such a world. Mars, the red planet, tells a story of transformation. Ancient riverbeds, dried lake basins, and mineralogical evidence indicate that water once flowed abundantly on its surface. Yet today, Mars is cold, arid, and barren, its thin atmosphere unable to retain heat. Exploration missions, from the Viking landers to the Curiosity and Perseverance rovers, have revealed sedimentary structures, organic molecules, and seasonal methane fluctuations, suggesting that while life may never have flourished as on Earth, the potential for microbial existence or the remnants of past habitability cannot be dismissed. Mars is a cautionary tale of planetary evolution, illustrating how delicate the balance of temperature, atmosphere, and geological activity must be to sustain life over billions of years. The outer planets are a different order of magnitude entirely. Jupiter, the largest planet, dominates the solar system with its immense gravity, influencing the orbits of other planets, shepherding asteroids, and perhaps protecting Earth from frequent catastrophic impacts. Its thick atmosphere, composed mostly of hydrogen and helium, is a theater of storms, including the Great Red Spot, a storm larger than Earth itself that has persisted for centuries. Saturn, adorned with its magnificent rings, is a laboratory of orbital mechanics, where countless icy particles interact in resonances and collisions, forming intricate patterns visible even from Earth. Uranus, rotating almost on its side, presents an axial tilt that is unique among planets, affecting seasonal dynamics and revealing the chaotic processes of planetary formation and collision history. Neptune, distant and cold, exhibits supersonic winds and intense storms, a planet whose very existence challenges early theories of solar system formation. Together, these giants anchor the solar system, their gravity sculpting not only the orbits of smaller bodies, but the distribution of asteroids, comets, and even distant dwarf planets. Moons across the solar system are no less remarkable. Earth's moon stabilizes our climate and influences tidal rhythms. Jupiter's moons, particularly Europa, Ganymede, and Io, are worlds of activity and potential. Europa's icy shell conceals a subsurface ocean, a tantalizing candidate for extraterrestrial life. Io, the most volcanically active body in the solar system, demonstrates the energy unleashed by tidal forces and internal heating. Saturn's Titan, with its dense nitrogen-rich atmosphere and liquid methane lakes, offers an alien landscape whose chemistry hints at complex organic processes. Even smaller moons captured or formed in situ act as records of past collisions, orbital resonances, and gravitational interactions, illuminating the complex evolution of planetary systems. Dwarf planets add further layers of complexity. Pluto, once considered the ninth planet, is a world of icy mountains, plains, and a tenuous nitrogen atmosphere that varies with its orbit. Eris, Makmak, Haumea, and Ceres challenge definitions of what constitutes a planet and reveal the diversity of bodies in the outer solar system. These icy and rocky worlds carry the history of solar system formation in their composition, orbit, and internal structure. They are remnants of a time when the solar nebula collapsed into planets and smaller objects, and studying them allows us to reconstruct conditions billions of years ago, offering a window into the earliest processes that shaped our cosmic neighborhood. The solar system's smaller constituents, asteroids, comets, meteoroids, are equally vital to understanding its architecture and evolution. The asteroid belt between Mars and Jupiter contains countless rocky fragments, remnants of bodies that failed to coalesce into planets due to Jupiter's gravitational influence. Comets, icy travelers from the Kuiper belt and Oort cloud, preserve primordial material from the solar nebula, their orbits occasionally bringing them into the inner solar system. Meteoroids, some resulting from asteroid collisions or cometary debris, enter Earth's atmosphere as shooting stars, delivering chemical elements and organic compounds that may have contributed to the emergence of life. These small bodies, though often overlooked, serve as time capsules, preserving the chemistry, dynamics, and processes of the solar system's formative years. Human understanding of these components has evolved dramatically over centuries, from early naked-eye observations to telescopic discoveries by Galileo, Huygens, and Cassini, and finally to modern space missions. Humanity has gradually catalogued the solar system in unprecedented detail. The development of spectroscopy revealed the compositions of planets and moons. Space probes, from Mariner and Voyager to New Horizons and Juno, have traveled to the furthest reaches of the system, transmitting images, measurements, and chemical analyses that reshape our understanding of planetary science. Each discovery uncovers new mysteries, from unexpected atmospheric dynamics to evidence of water or organic molecules, revealing the solar system as a dynamic, evolving environment rather than a static arrangement of celestial bodies. Above us stretches a darkness so vast it defies comprehension, a black canvas sprinkled with infinite points of light. To gaze upward is to confront the immeasurable, to realize that every star, every speck of light is a distant sun, a system of worlds, a fragment of history unfolding across billions of years. Space is not merely emptiness, it is a profound mystery, a silent force, an ever-expanding arena of energy, matter, and motion. It is a place where time stretches and contracts, where light takes millions and billions of years to traverse the distances we attempt to measure with numbers that lose meaning against its enormity. Humanity has always looked upward, drawn by curiosity, fear, and wonder. The night sky has been our first library, each constellation a story, a calendar, a map of myths. Yet behind these myths lies a reality far stranger and more intricate than anything imagination alone could conceive. Why does space fascinate us? Perhaps it is because it holds the ultimate unknown. On Earth, every question has a measure, a solution, a boundary. But in the cosmos, boundaries blur. Space challenges our intuition, our understanding of physics, and our very concept of existence. It is a laboratory of extremes where temperatures plunge to near absolute zero and rise beyond millions of degrees, where matter is compressed into densities so extreme that atoms collapse and time itself slows near colossal gravitational wells. To study space is to confront forces that dwarf human experience, to measure scales of distance, mass, and energy that defy normal perception. Yet the very incomprehensibility of it draws us in, igniting our desire to explore, to understand, to reach beyond the confines of our planet. Humanity's fascination with the stars has deep roots. Ancient civilizations meticulously charted their movements. The Babylonians recorded planetary paths with astonishing precision, aligning their lives with the celestial rhythms. Greeks and Egyptians pondered the mechanics of the heavens, theorizing spheres, orbits, and divine structures that gave order to the chaos above. In every era, the sky was more than a backdrop. It was a source of questions that shaped mathematics, astronomy, and philosophy. As tools improved and telescopes emerged, humans discovered moons around Jupiter, the rings of Saturn, and the phases of Venus, gradually peeling back the layers of mystery, revealing a universe governed not by mythology, but by laws of physics and chemistry, laws that could be observed, calculated, and understood. The dawn of modern space exploration transformed human perception once more. With each satellite launched, each telescope extended beyond the atmosphere, and each robotic probe traversing the solar system, the cosmos became increasingly tangible. The Hubble Space Telescope revealed galaxies forming in distant epochs, nebulae where stars ignite, and supernova remnants where matter is returned to space. These images are more than pictures. They are portals to the past, glimpses of events that occurred billions of years ago, long before life existed on Earth. Space has become a narrative of time itself, a record of creation, destruction, and transformation writ across the darkness, waiting for humanity to read its story. Space is not just distant, it is dynamic. Stars are born and die, massive bodies collide, black holes distort the fabric of reality, and invisible forces sculpt galaxies over unimaginable timescales. Even the emptiest regions of interstellar space are not voids, but host a tenuous gas, magnetic fields, cosmic rays, and dark matter whose presence governs the motion of stars and galaxies. The vacuum is a stage for physics at its most extreme, a place where quantum fluctuations, gravitational waves, and high-energy particles interact in a dance both subtle and catastrophic. To venture into space intellectually is to confront these extremes, to measure phenomena that challenge comprehension, to expand the human mind to scales and intensities far beyond daily experience. Yet space fascinates not just because of scale or danger, but because of potential. It is a repository of questions about origin, purpose, and destiny. What forces shaped our galaxy? Are there other worlds like Earth? Can life exist elsewhere, or are we the product of an improbably precise set of circumstances? Exploration, both observational and robotic, seeks answers. Mars rovers analyze sediments that may have held water. Telescopes measure atmospheres of exoplanets light years away. Even the tiniest asteroid traveling silently through the solar system carries clues to the primordial chemistry that birthed our sun, planets, and perhaps even life itself. Every discovery deepens our understanding, but also opens new mysteries, reinforcing the paradox that in the vastness of space, knowledge is both precious and perpetually incomplete. Humanity's journey into space is also philosophical. To comprehend the cosmos is to confront human significance, to balance awe against humility. Our lives, measured in decades, unfold against a backdrop of billions of years. Our species, fragile and young, orbits a star in a galaxy among billions, a speck of consciousness amidst a universe of magnitude that challenges comprehension. Yet this realization is not despairing, it is empowering. The active observation of understanding transforms scale into insight. By mapping the heavens, we locate ourselves not as victims of cosmic chaos, but as participants in a grand structure capable of curiosity, discovery, and reflection. Space compels us to imagine the unimaginable. It invites visions of worlds beyond our reach, of phenomena that defy earthly logic. Black holes whose gravity halts time, neutron stars spinning at incredible speeds, quasars emitting energies that dwarf entire galaxies, and potential wormholes bridging vast distances instantaneously. It reminds us that the universe operates under principles both elegant and violent, a system of cause, effect, and chance whose narrative extends beyond what we can see, yet whose effects touch us subtly every day, from the tides on Earth to the sunlight that warms our planet. The final frontier is not merely a destination, it is a question. It is the unknown made tangible, the vastness that humbles and inspires. It is a call to explore, to understand, and to measure human potential against the cosmos. The awe it inspires is inseparable from the knowledge it demands. And in that tension between wonder and reason, humanity finds both purpose and perspective. To look outward is to look inward, to confront our limitations and possibilities, to recognize that the universe is larger, stranger, and more magnificent than any story we could imagine. Space is the final frontier, not because it is unreachable, but because it constantly challenges us to reach further than we ever thought possible. The formation of the universe. Before there was light, before there was space as we know it, before even time itself had meaning, the universe existed in a state that defies human imagination. It was a singularity, a point of infinite density and heat, where the laws of physics themselves were compressed into a form beyond comprehension. This was the origin of everything, the moment that would eventually give rise to stars, galaxies, planets, and life. The story of the universe begins here, in that unimaginable infinitesimal state, and yet it is a story written in time, energy, and matter that stretches across billions of years. A narrative of creation unfolding with both violence and elegance. The Big Bang Theory is humanity's most precise explanation of this origin. Approximately 13.8 billion years ago, space itself began to expand. It was not an explosion in the conventional sense, but the sudden stretching of all dimensions, the rapid inflation of space, carrying with it energy and the seeds of matter. In the first moments, the universe was an almost incomprehensible fireball of particles, radiation, and fundamental forces intertwined in a cosmic dance. Temperatures were so high that even quarks and gluons, the constituents of atomic nuclei, could not form stable matter. Yet within this chaos, the initial fluctuations, the tiniest variations in density, laid the blueprint for everything to come. These quantum ripples, microscopic and invisible at the time, would become the scaffolding for galaxies, clusters and superclusters billions of years later. Within the first few minutes, the universe cooled just enough for protons and neutrons to combine, forming the first atomic nuclei, predominantly hydrogen and helium, with traces of lithium. This process, known as nucleosynthesis, produced the simplest elements, establishing the chemical foundation of all future stars, planets, and life. For hundreds of thousands of years, the universe remained opaque. a hot fog of photons and charged particles where light could not yet travel freely. Then, in a monumental transformation called recombination, electrons combined with nuclei to form neutral atoms, allowing photons to move unhindered. This event created the cosmic microwave background radiation, a faint afterglow that astronomers detect today, stretching across the sky and providing a snapshot of the universe in its infancy. As the universe expanded, matter began to coalesce under gravity. Dense regions grew denser, drawing in gas and dust, while surrounding voids emptied. These fluctuations seeded the formation of the first stars and galaxies. Within the first few 100 million years, clouds of hydrogen collapsed under their own gravity, igniting the nuclear furnaces of the earliest stars. These stars were massive, short-lived and furious, burning through their fuel rapidly and dying in spectacular supernova explosions. These explosions were not mere finales, they were the first forges of heavy elements. Carbon, oxygen, iron and other elements essential to planets and life were scattered across the cosmos, enriching the interstellar medium and setting the stage for subsequent generations of stars and solar systems. Galaxies began to form as gravity gathered stars into vast rotating structures. Some took the shape of spirals, their arms swirling with young, blue stars and nebulae, while others formed elliptical, irregular configurations. Galaxies were not isolated. They interacted, collided, and merged over millions and billions of years. These cosmic encounters drove bursts of star formation, reshaped structures, and built the large-scale filaments and voids that now define the observable universe. The Milky Way, our home galaxy, emerged as one of countless galaxies forming a cosmic web, its spiral arms hosting billions of stars, clusters, and stellar nurseries. Within these galaxies, stars continue to evolve. Clouds of gas, remnants of previous supernovae, and primordial material combined under gravity to form protoplanetary disks. Spinning clouds of dust and gas where new stars and planetary systems could take shape. This cycle of birth, death, and renewal is the heartbeat of the universe. Each star that ignites not only illuminates its surroundings, but transforms the chemical environment, producing elements necessary for planets and, eventually, life. The universe in this way is both a forge and a library, storing the history of matter in its structures and compositions. The first galaxies were unlike the Milky Way we see today. They were chaotic, irregular, and compact, often forming stars at astonishing rates. Observations of distant galaxies allow astronomers to look back in time, seeing these ancient structures as they were billions of years ago. By studying them, we understand the processes that shaped large-scale cosmic structures, the influence of dark matter, which binds galaxies and clusters with gravity despite being invisible, the role of dark energy driving the accelerated expansion of space itself, and the intricate ballet of gas inflow, star formation, and feedback from supernovae and black holes. Each of these forces contributed to a universe that is both structured and dynamic, predictable yet full of surprises. Stars forming in these galaxies are the engines of the universe. Their life cycles dictate the distribution of elements, the dynamics of galaxies, and the conditions necessary for planetary systems. Massive stars live fast and die young, scattering heavy elements, while smaller stars, like our Sun, burn steadily for billions of years, providing stable environments for planets. The interplay of mass, composition, and gravity governs a star's behavior, producing an extraordinary diversity of stellar types, red dwarfs that burn quietly for trillions of years, luminous blue giants that blaze intensely, and binary systems whose interactions lead to nova and supernova events. These stellar processes are not distant abstractions, they underpin the very matter that forms worlds and, ultimately, life itself. The formation of planets follows naturally from the evolution of stars. Around newborn stars, protoplanetary disks condense into planetesimals, rocky and icy bodies that collide, merge, and accrete into larger structures. In some systems, giant planets dominate, reshaping the orbits of smaller worlds and shepherding debris. In others, rocky planets form closer to the star, potentially within habitable zones where liquid water can exist. Our own solar system, born from such a disk 4.6 billion years ago, is a product of these universal processes: a star, 8 planets, numerous moons, and countless smaller objects, all arising from the remnants of earlier generations of stars. Understanding the universe's formation requires piecing together evidence from multiple disciplines. Cosmic microwave background measurements reveal the universe's conditions at the dawn of time. Spectroscopy of distant galaxies shows the chemical evolution of stars across billions of years. Observations of star-forming regions, like the Orion Nebula, allow us to witness stellar birth in progress. Meteoritic studies provide a record of solar system formation, revealing isotopic ratios and primordial chemistry that confirm theories of accretion and early nuclear processes. Each piece of evidence, like a thread in a tapestry, contributes to a coherent narrative of cosmic evolution. Yet even with all we know, profound mysteries remain. Dark matter constitutes most of the universe's mass, yet it interacts only through gravity, remaining invisible to detection. Dark energy drives the acceleration of cosmic expansion, its nature entirely unknown. The earliest moments of the universe during inflation lie beyond direct observation, known only through theoretical extrapolation and indirect evidence. These enigmas remind us that while the universe is intelligible in many ways, it is far from fully understood, a frontier not just of space, but of knowledge itself. The formation of the universe is more than a story of matter and energy. It is the story of time, causality, and transformation. From a singularity emerged space itself. From fluctuations arose galaxies. From stellar furnaces came the elements that compose planets, moons, and living organisms. The universe is a dynamic, interconnected system, governed by principles that can be understood, yet infinitely complex in their interplay. To study its formation is to study existence itself, to trace the cosmic origins of the world we inhabit, and to confront the profound question, from such extreme beginnings, how did complexity, structure, and life arise? The universe's story is ongoing. Galaxies continue to merge, stars continue to form and die, and space itself continues to expand. Every photon that reaches Earth, every cosmic ray that passes through the planet, every orbiting planet, asteroid, and comet carries echoes of these primordial events. In studying the formation of the universe, humanity is not merely looking outward, it is looking backward and inward, tracing the sequence of cause and effect that ultimately led to life, consciousness, and our ability to comprehend the cosmos. The Big Bang was not simply an event, it was the opening chapter of a narrative that continues, and by observing, measuring, and theorizing, we participate in that story, our solar system. The solar system is not merely a collection of celestial bodies, it is a dynamic, intricate system, a cosmic clockwork orchestrated by gravity, energy, and time. At its center burns the sun, a medium-sized star whose light and gravity govern the rhythm of the planets, moons, comets, and asteroids that revolve around it. To understand the solar system is to understand the forces that sculpt worlds, the chemical processes that create elements, and the delicate balances that allow life to emerge on at least one small, fine, pale blue dot among countless others. The Sun dominates not only in mass but in influence. Comprising more than 99% of the solar system's mass, it dictates the motions of planets and shapes the environment of space itself. Its nuclear furnace converts millions of tons of matter into energy every second, releasing light, heat, and charged particles that reach every corner of the solar system. The solar wind, a continuous stream of ionized particles, sculpts planetary magnetospheres, drives auroras on Earth and other planets, and interacts with comets to create their luminous tails. The Sun's behavior is cyclic. Sunspots and solar flares wax and wane, reflecting shifts in its magnetic field and sending subtle and sometimes violent ripples across the planets it illuminates. Mercury, the smallest and closest planet to the Sun, is a world of extremes. Its daytime temperatures soar into searing heat, while its nights plunge into freezing cold. Its cratered surface tells a story of relentless bombardment in the early solar system, while evidence of ancient volcanic plains revealed internal processes long extinguished. Mercury's weak magnetic field hints at a partially molten core, a remnant of geological vigor, and its orbit, unusually eccentric and inclined, illustrates the gravitational influence of the Sun and neighboring planets. Venus, often called Earth's twin, is a planet transformed by its atmosphere. Thick clouds of carbon dioxide and sulfuric acid trap heat in a runaway greenhouse effect, producing surface temperatures hotter than Mercury, despite its greater distance from the Sun. Its volcanic plains and tesserae indicate a geologically active past, though whether it still hosts any internal dynamism remains uncertain. Venus is a warning of planetary fragility, demonstrating how small shifts in atmospheric composition and solar radiation can irreversibly alter a world's climate and geology. Earth, our home, is a world of balance. Its liquid water, oxygen-rich atmosphere, and stable climate are the result of precise conditions, including its position in the habitable zone, the moderating influence of the Moon, and the protective shield of its magnetic field. Earth's geology cycles carbon and nutrients, stabilizing the climate over millions of years. Life, emerging over billions of years, has both adapted to and altered the planet, creating a feedback loop between biology and environment, unique in the known solar system. The Earth-Moon system is itself a testament to cosmic accidents and forces. A colossal impact early in Earth's history produced the Moon, which stabilizes Earth's axial tilt, moderates tides, and may have influenced the evolution of complex life. Mars, the red planet, embodies both promise and desolation. Ancient riverbeds and lake beds, mineral deposits, and polar ice caps all speak of a wetter, warmer past. Mars has lost most of its atmosphere, leaving a cold desert landscape, yet evidence suggests episodic water flows and chemical processes that could have supported microbial life. Its volcanoes, including Olympus Mons, the tallest mountain in the solar system, reveal the scale of its geological activity, while Valles Marineris, a canyon system thousands of kilometers long, demonstrates the planet's tectonic and erosional history. Mars is a laboratory for understanding planetary evolution, illustrating the fine line between habitability and sterility. The asteroid belt lying between Mars and Jupiter is a region of fragments and relics. These are remnants of early planet formation, bodies that never coalesced into a larger planet due to Jupiter's immense gravity. Asteroids vary from metallic cores to carbon-rich rubble piles, and studying them allows us to peer into the primordial chemistry of the solar system. They are messengers from a time before planets fully formed, preserving the isotopes and mineralogy of the early Sun's protoplanetary disk. Jupiter, the giant, dominates the solar system with its mass and gravity. Its immense size affects the orbits of nearby asteroids and protects the inner planets from many potential catastrophic impacts. Its atmosphere is a turbulent landscape of hydrogen and helium marked by the Great Red Spot, a storm larger than Earth that has raged for centuries. Jupiter's magnetic field is vast and intense, capturing radiation belts and interacting with its moons. Speaking of moons, Jupiter hosts a complex system of satellites. Europa hides a subsurface ocean beneath an icy shell. Ganymede, the largest moon in the solar system, has its own magnetic field, and Io is the most volcanically active body in the solar system, heated by tidal interactions that exemplify the power of gravitational forces. Saturn, adorned with its intricate rings, is another colossal gas giant. Its rings are composed of countless icy particles shaped by gravitational resonances with moons and each other. Saturn's moons are equally fascinating. Titan possesses a thick nitrogen atmosphere and hydrocarbon lakes, presenting a chemical complexity unlike anywhere else. while Enceladus ejects plumes of water vapor and organic compounds, suggesting a subsurface ocean heated by tidal forces. These moons challenge our assumptions about where and how life might arise. Uranus and Neptune, the ice giants, occupy the outer reaches of the solar system. Uranus rotates almost on its side, creating extreme seasonal variations, while Neptune exhibits supersonic winds and intense storms, an active and dynamic world far from the sun's warmth. These distant giants, composed of water, ammonia, methane, and other volatiles, reveal the diversity of planetary formation processes and the influence of distance, composition, and mass on planetary evolution. Beyond the planets lie the dwarf planets and the Kuiper Belt, home to Pluto, Eris, Haumea, and countless icy bodies. These remnants of solar system formation are frozen time capsules, preserving conditions from the earliest era of planetary accretion. Comets, originating from the Kuiper Belt and or cloud, are icy travelers whose elliptical orbits sometimes bring them close to the sun, creating spectacular tales of gas and dust. They are chemical relics containing water, organic compounds, and other molecules that may have been delivered to early Earth, seeding the conditions for life. Even the seemingly empty regions of space between these objects are dynamic. Dust, cosmic rays, magnetic fields, and the solar wind fill the interplanetary medium, shaping planetary atmospheres, eroding surfaces, and driving space weather that impacts both robotic and human explorers. The solar system is a theater of interactions, of subtle and violent forces, where gravity, radiation, and chemistry operate on scales that dwarf human experience yet are intimately connected to the conditions on Earth. Exploration of the solar system has transformed humanity's understanding, from early telescopic observations to the Voyager missions venturing beyond the planets, from orbiters mapping atmospheres to rovers analyzing soils. Each advance has revealed unexpected complexity. Mercury is not a simple cratered rock, but a dynamic world with magnetic anomalies. Mars is not a barren desert, but a planet shaped by water, wind, and geological forces. Jupiter and Saturn are not just gas spheres, but laboratories of storms, radiation, and tidal forces, their moons offering potential habitats beyond Earth. The solar system is also a record of the processes that govern all planetary systems. By studying its formation, evolution, and current state, scientists can extrapolate to distant exoplanetary systems. Patterns emerge. Massive planets often shape smaller ones. Protoplanetary disks produce both rocky and icy worlds. Collisions and gravitational resonances sculpt orbits and moons. In understanding our own solar system, humanity gains insight into the potential ubiquity or rarity of planets like Earth, and into the broader story of the universe itself. In the end, the solar system is a delicate balance of chaos and order. Gravity maintains the architecture of planets and moons, while collisions and radiation drive transformation. Chemical processes in stars and planetary surfaces create the diversity necessary for planets, atmospheres, and life. It is a system in motion, a history written in rock, ice, gas, and light, a laboratory for understanding our origins and destiny. And as humanity looks outward, sending probes, rovers, and telescopes, it becomes not only a story of observation, but of participation, a cosmic dialogue between the observer and the observed, where each discovery illuminates both the universe and our place within it, stars and their life cycle. Every star in the night sky tells a story, a narrative of birth, transformation, an eventual death that spans millions or billions of years. Stars are not mere points of light, they are furnaces of creation, engines of chemistry, and architects of the universe itself. To study a star is to study the history of matter, energy, and life, for the elements forged within these glowing spheres are the building blocks of planets, atmospheres, and biological life. The life of a star begins in obscurity, in vast clouds of gas and dust called nebulae, which drift silently through the galaxy, often invisible until illuminated by newborn stars. Nebulae are chaotic regions, turbulent and dense, where gravity competes with pressure, magnetic fields, and turbulence. Within these clouds, small fluctuations in density occur, often triggered by shockwaves from nearby supernovae or collisions with other clouds. These denser pockets begin to collapse under their own gravity, drawing in surrounding gas and dust. As the material condenses, it heats, forming a protostar at the center of a spinning disk of gas and solids. The protostar is hidden beneath layers of dust, yet within it, nuclear fusion is on the verge of ignition, the spark that will transform it from a cloud of matter into a radiant star. The next stage, the main sequence, is where a star spends the majority of its life. Hydrogen atoms in the core fuse into helium, releasing energy that radiates outward and balances the inward pull of gravity. The star achieves hydrostatic equilibrium, a delicate balance between pressure and gravity, maintaining stability for millions or even billions of years depending on its mass. Low-mass stars, such as red dwarfs, burn slowly and can persist for trillions of years, long beyond the current age of the universe. Massive stars, by contrast, burn intensely, fusing heavier elements rapidly, their lifespans measured in mere millions of years. These main sequence stars are the engines of galaxies, producing light, heat, and the radiation that influences surrounding interstellar matter. Eventually, hydrogen in the core is exhausted, and stars evolve into red giants or supergiants, expanding dramatically as fusion continues in shells around the core. The outer layers cool and redden, while the core contracts and heats, allowing the fusion of heavier elements like carbon, oxygen, and neon. In massive stars, this process continues through silicon and iron, producing elements essential to planets and life. The star's evolution depends on its mass, for it is mass that dictates whether a star ends its life quietly as a white dwarf or cataclysmically as a supernova. Supernovae are among the most violent and transformative events in the cosmos. When the core of a massive star collapses under its own gravity, the outer layers rebound in an explosion of unimaginable energy, briefly outshining entire galaxies. Supernovae disperse heavy elements into space, enriching the interstellar medium with the material necessary for future stars, planets, and life. The remnants of these explosion neutron stars, pulsars, and black holes test the extremes of physics where gravity warps space and time and densities surpass anything found on Earth. The death of a star is not the end of its influence. It is a catalyst, seeding the next generation of cosmic creation. White dwarfs are the final stages of low-mass stars, Earth-sized remnants of former main sequence stars composed primarily of carbon and oxygen. They no longer sustain fusion, yet their heat and radiation slowly fade over billions of years. Neutron stars, born from more massive progenitors, are extraordinary in their density and magnetic strength. A teaspoon of neutron star matter would weigh billions of tons, and their rapid rotation produces pulsars, beacons of radiation sweeping across space with incredible regularity. Black holes, the ultimate endpoint for the most massive stars, represent singularities where gravity overwhelms space and time, creating regions from which nothing can escape, not even light. The life cycles of stars are intimately connected to the chemical evolution of the universe. Hydrogen, helium, and trace lithium emerged from the Big Bang, but every element heavier than that owes its existence to nuclear fusion within stars. Carbon, nitrogen, oxygen, iron, and all other elements essential to planets and life were created in stellar cores or in supernovae. Every atom in our bodies, in the soil beneath our feet, and in the air we breathe was forged in the furnaces of ancient stars. In this sense, humanity is not separate from the cosmos. We are a direct product of stellar evolution, the living embodiment of processes that began billions of years ago. Binary and multiple star systems add further complexity to stellar evolution. Stars orbiting each other exchange mass, sometimes triggering nova or supernova events, creating exotic objects such as accretion disks and X-ray binaries. Stellar interactions can strip away outer layers, ignite fusion in unusual patterns, or even eject stars entirely from galaxies. These systems reveal that stellar evolution is not isolated, but is profoundly affected by environment, motion, and gravitational dynamics. The study of stars has a long history. Ancient astronomers tracked their motions across the sky, forming calendars, myths, and early models of the universe. With the telescope, new dimensions were revealed: variable stars that pulsate in brightness, binary systems whose masses could be measured, and distant suns whose light told of chemical compositions and temperatures. Modern astrophysics uses spectroscopy, photometry, and space-based observatories to probe stellar interiors, measure fusion rates, and detect exoplanets. By observing stars in all stages of life, scientists have pieced together the universal narrative of stellar birth, evolution, and death. Stars also sculpt their galactic neighborhoods. Stellar winds, radiation, and supernova shocks drive turbulence in molecular clouds, triggering new waves of star formation. In this way, galaxies are ecosystems, where stars are both creators and destroyers. The end.